In this video lecture, we'll talk about independence of sigma algebras. To motivate the definition of independence of sigma algebras, let us recall the following definition from probability and mathematical statistics modules that we took before. With three events, we say that they are independent. It can be, I'm stating for three, but it could have been any other number. If the probability of B1 occur and B2 occur and B3, all of them occur, is the product of each one of them, where B can be either omega or A3. So B3 can be both, which means if I take omega, this is the same as not including B3 and not including B3 here and here in case it is omega. In case of, we can also ask B3, we can also ask this identity to hold when B3 is the empty set. This identity holds trivially on the empty set because when we take the empty set here, this intersection will be empty, this probability will be 0, and this probability here will be 0, so the product will also be 0. So this always holds if I take B3 to be the empty set. Also, if this holds when B3 equals A3, then I can take A3 complement, and this will just mean that here I get P of B2, B1, P of B2 minus P of B1, P of B2, P of B3, and if I assume that this second term here is the probability of the intersection of A1 and B2 and B3, then what you will get here on this side, it will be exactly the probability that B1 and B2 and omega occur. This will correspond to this because we are assuming this holds when B3 equals omega, minus the probability that B1, A1, and A2 and A3 occur, which is exactly the probability that A1 occurs and A2 occurs and A3 does not occur. Okay, this is just to say if this is true when we remove A3 from the product, if this is true when we remove A3, and if this is true when we put A3 here, then this will also be true when we put A3 complement. And moreover, it's also always true when we put A3 to be the empty set, because then we get 0 on both sides. So I'm just reformulating in a more fancy way what it means for three events to be independent. They are independent. The three of them are independent if this probability will factorize by for any choice of B3 to be empty, A3, A3 complement, or omega. And also any choice of B2 to be empty, A2, A2 complement, and omega, etc. And this is just a reformulation, a more fancy reformulation. It sounds fancy, but it's actually more convenient because this one has more structure. What is this family of sets here? This family of sets here, well, it is just the family AJ alone, if we want. It's the sigma algebra generated by that family. And this is what it means for three events to be independent. For these three events to be independent, it's not just that probability of A1 intersection A2, it factorizes the probability of A1 intersection times the probability of A2 and the probability of A2 intersection A3 factorizes is not, this would be pairwise independence, and pairwise independence is different, as we already know, from general independence. Okay, and then also 1 is independent of 2, 2 is independent of 3, 3 is independent of 1. So basically it's saying the probability factorizes to these sets, to any pair of these sets, but not just the pairs. These would be pairwise independent, but we want them to be collectively independent or stochastically independent. So we also need that the probability of A1 intersection A2 intersection A3 to factorize. And well, if we had more than 3 sets, what we would be requiring really is that for any subset of indices, the probability would factorize. So here we have a set of indices. Okay, we have indices j, which can be 1, 2, or 3. If we had more indices, what we would require is that probability that the intersection of j over any set A of a, let's not use A, let's use a maybe capital J of AJ should be equal to the product over J of the probability of AJ. This for every J, a subset of this set of indices. So this would be the proper formulation, and it is captured by these choices here. So we don't need empty. With empty, all this equality becomes trivial. But with omega means that J is not in the set J. Means I'm not including this set here in this intersection. I'm not including this set here in this product. That's when I choose omega to place here instead of AJ. Okay, so I have this choice, AJ or omega. This has a lot more structure, and this justifies the definition of independent sigma algebras. We have a probability space, and we have G1, G2, G3, Gn, a collection of sub-sigma algebras. What's a sub-sigma algebra? It's a sigma algebra which is contained in F. Okay, sub-sigma algebra means exactly G1 is a sigma algebra, and G1 is contained in F, meaning any set which is measurable with respect to this sigma algebra is also measurable with respect to this sigma algebra, which means any B that is a member of this family must also be a member of this family. Okay, you have a collection of sub-sigma algebras. Here I just showed 3 sub-sigma algebras. Okay, you just think of a very simple probability space. You can think tossing a coin. So it's a probability space that has 8 points. If you toss the coin 3 times, and you want to talk about the independence of coming heads or tails in those 3 tossing of coins, then well, here are smaller sigma algebras. Yeah? If you toss 3 coins, omega has 8 elements, and the sigma algebra has quite many more than 8 elements. It has 256 different sets in the sigma algebra, and we can consider these much smaller sigma algebras that only have 4 sets in them instead of 256, and we can wonder what is how probability will respond to sets in those sigma algebras. And this is the definition of independent sigma algebra. The definition of independent sigma algebra is when The probabilities will factorize whenever we take intersections of members of this sigma algebra. And we take A1 from the first sigma algebra, and we take each other set from the corresponding sigma algebra. The last set, AN, we take it from GN. And the probability that all these events occur is equal to the product of the probabilities of each of these events. Okay? And that's when we choose each AI to be in the corresponding GI. So this is a very sophisticated definition. It's a bit scary at first, but this is just more convenient. This is just making use of this formulation of independence with more structure in it.